Okay. Yeah. Yeah. Is on. Yeah. I start. Okay. Yeah. Okay. So, welcome back. Let's see where we are. So yesterday we derived this spectrum of low-lying excitations of this XX chain, which was the Hamiltonian for delta equal to 0. And what we observed was that these excitations are gapless, and they correspond to a linear dispersion at low energies, yeah, which we just got by linearizing the lattice dispersion around the Fermi points. Okay, and these observations tell us immediately that this entire spectrum has to arise just that there must exist a field theory limit, a quantum field theory limit of this lattice model that precisely reproduces the spectrum that we derived yesterday. And so there exists a QFT limit that reproduces this. And this QFT limit we will now derive by elementary means. That's a very simple calculation. So what we do is we take the continuum limit of the lattice model. And this procedure is very general. So what we do is we start with the lattice Hamiltonian. Now in presence of the interactions, and we say, okay, so that's a free part plus the interactions, so which is the piece proportional to delta. So H free is simply minus j over 2 sum over j, c dagger j, cj plus 1 plus Hermitian conjugate. And then here I have a chemical potential term, and in the chemical potential term I take into account some effects of the interactions. I don't have to do that, but well, okay, I might as well. Plus 2j delta nj and so this I call h prime, and the interactions then I rewrite like so. Nj minus the ground state average of Nj times Nj plus 1 minus ground state average of Nj plus 1. Okay, so I've done a very trivial kind of rearrangement. So I've, roughly speaking, normal ordered the interaction term, but if you combine all the pieces proportional to this expectation value, it just drops out. Yeah, so what you get here precisely compensates this one. Okay. And then there's a constant contribution to the Hamiltonian, which I don't care about. Okay, so now let's look at this free part. H free we looked at yesterday, essentially. Yeah, so instead of H prime, we had H yesterday, but of course all the steps go through. So, which means the ground state is obtained by filling a Fermi C between some Fermi momentum and minus the Fermi momentum, and Kf is arc cos H prime over J. So that's what we had yesterday. And then this expectation value, okay, so Nj, if you wish, in the free theory is just Kf over pi. We also had that yesterday. And now combining these two observations, you get a very simple self-consistency equation. So you get Kf from here is equal to arc cos. And then here I have the H prime, which is written there. H over J minus delta plus 2 delta Kf over pi. Yeah, so this is just what we have here. Okay, and then you can solve this for Kf. Yeah. So for example, in a power series, so this will be arc cos H over J, and then you have something like minus delta square root 1 minus H squared over J squared, 1 minus 2 divided by pi arc cos H over J plus delta squared dot dot dot. Okay? Okay, so far I haven't really done anything. Yeah, so I have used what we did yesterday and taken into account some effects of the interactions. So now what I want to do is I want to project this lattice Hamiltonian, both the free part and then the interaction part, to the low energy degrees of freedom. And so the low energy modes they are located at momenta k or kn is approximately equal to plus or minus kf. Yeah, as we saw yesterday. And so just recall that the lattice fermion operators were given in terms of the momentum modes by this. Okay? And now what we want to do is we want to project these operators onto the low energy modes. And the low energy modes, they appear when Kn is approximately plus or minus Kf. Okay? And that then tells you that the low energy projection will have a piece which is proportional to e to the minus ikf, approximately, yeah, because the k's are approximately plus or minus kf, and another piece which is proportional to e to the plus ikf times j, yeah. And so we can so now project to low energy modes, and that gives us Cj. I should replace by some dimensionful quantity, and why I do that I just will tell you in a moment. So then here I put a Fermi field, which I call R of x, and here I collect all the momentum modes from here, which give me an oscillating factor that is roughly e to the I kfx. And then I have the other part, which is this. Okay, where A naught is the lattice spacing, so x I set equal to j times A naught. Okay, and so the lattice spacing now has dimensions of meter, so it's a dimensionful quantity.
Just to make sure I understand, in the original Hamiltonian, are the expectation values taken with respect to the free theory for n to j?
Yeah, so I take them with respect to the free theory, but I have taken into account the interaction in some kind of mean field approximation, some kind of self-consistent mean field approximation, which then allows me to capture some effects of delta, if you wish, for not very small values of delta. I don't have to do that, but I can do it free of charge, so I did it. Yeah. If you don't like that step, you don't have to normal order the interaction. You can proceed otherwise, then this will come back a little bit later. Yeah. Yeah, so where were we? Yeah, so this is kind of one of the most important formulas. Yeah. So x is j times the lattice spacing, so x has dimensions of meter. Now r of x will be some fermion field, okay? And as such, it should have fermionic anti-commutation relations. And in the fermionic anti-commutation relations, you get on the right-hand side a delta function of x and y, yeah, which is dimension 1 over meter. So that means these Fermi fields, they have dimension 1 over square root of meter, okay? But the CJs, of course, are dimensionless, which is why I have introduced here this dimensionful prefactor. Okay? Yeah. No, it's not an ansatz. I mean, so I try to motivate it. So what I said is this is the full lattice fermion operator. But then I said these in the free theory, these are the momentum modes, yeah, and all of these low-lying excitations we constructed yesterday, they're given basically in terms of Fock states of C dagger of K, where the low-lying excitations basically come from momentum modes in the vicinity of Kf, in the vicinity of minus Kf. So what I do basically, to do the low energy projection, I restrict this sum to two shells, one around Kf and one around minus Kf. Okay? But when I do that, what do I get? I get something here on the right-hand side, which always has this factor e to the I kfx, plus some small deviation from kf, because those are the low energy modes. But these describe kind of like smooth, long wavelength physics, and that I incorporate in this Fermi field, which describes this smooth, long wavelength physics. And so this is the other contribution, which is e to the minus I kfx. If you wish, yeah, exactly. Okay. So this is now, if you wish, how you obtain this right and left moving Fermi fields. And now you just plug this into the Hamiltonian. So let me see. Okay, so before I do that, let me make a couple of comments. So this introduces a cutoff in momentum space. Yeah, because I've selected basically some shells around kf and minus kf as only modes plus or minus kf minus lambda less than k less than plus or minus kf plus lambda are retained. Okay, so that's a fundamental feature, if you wish, when you take a continuum limit. So you no longer describe all of the physics of the lattice model, so you describe only the physics at energies that are much less than the cutoff or large distances, yeah, so that are much larger than some short distance cutoff. And so as we remove small momentum modes, we no longer can describe physics on the lattice scale. And the lattice scale is A naught, but only distances x which are much larger than the lattice spacing. Okay, so this is a fundamental feature of any quantum field theory limit.
When you went from CJ
Yes.
to the sum to the continuum expression, doesn't KF have to pick up some dimensionality because you went from
So what I have done, yeah, so thanks for the question. So here, I have used capital KF. It's a dimensionless quantity, yeah, because you see here there's no dimension. On the other hand, here it's little kf, yeah, so that is dimension full because x is dimension full. So I should have added here little kf is simply kf divided by a naught. So thanks for asking that. Well spotted. Yeah. So it's just in the field theory space has dimension always, whereas on the lattice model you don't, and you just have to restore all the dimensionful quantities. But you do it by inspection, basically just sticking the lattice spacing back where required. Any other questions? Okay. Now let's see what happens to the Hamiltonian. So now the nice thing about this boxed formula is you can take this now, well, essentially literally and use to compute. So let's see, let's look at the hopping term. Let's see what happens to this. Okay, so if I project to low energy, I just use this formula now, nothing else. So what do I get? I get A naught sum over J. And here I get something like right dagger of x, right of x plus A naught. And here I get e to the I kf A naught. Yeah, because, so this goes into x is j A naught. This goes to x plus A naught is equal j plus 1 A naught. Okay? And then you see, because of the oscillating factor, they don't precisely cancel because this one is shifted, so you pick up the extra e to the I kf A naught. All right, and then you just carry on, plus left dagger of x plus A naught, e to the minus I kf A naught. And then we have backscattering terms, so e to the 2I kf x plus I kf a naught left dagger of x, right of x plus a naught. And I have one more, plus e to the minus 2I kfx minus I kf a naught left, right dagger of x left of x plus a naught. So that's what I get by just multiplying out. That's all I've done. All right? Okay. Because in terms of the Fermi sea, it corresponds to making a hole at one side and making a particle on the other side. It's like these 2kF processes we talked about yesterday. Yeah, because you see, R basically is at one side of the Fermi sea and L is on the other side of the Fermi sea because of this decomposition here. Yeah? Okay? So you see, things like these, they would correspond to making a hole close to KF and then putting a particle also close to a KF, yeah? And the other ones you go across the Fermi sea, yeah? Okay, so now I have multiplied out, and now we just tailor, so formally speaking, now what we do, now take the limit, so there is a precise definition of the scaling limit. So we take the limit of the lattice spacing going to 0, yeah, because we want to describe quantum field theory. But then we also take the limit of J goes to infinity. Yeah, so J is the exchange constant in the Hamiltonian. And we keep the Fermi velocity, which is J A naught sine Kf A naught fixed. So that is the precise definition of the scaling limit. Because otherwise the Fermi velocity would not be finite in the limit where I take the lattice spacing going to 0. Yeah, so the Fermi velocity is a physical property. It's the velocity of propagation of waves at low energies. Yeah, and so formally speaking, you take this limit. What it means in practice, I was just about to explain, is you have this dispersion. Yeah, so here is K minus Kf, Kf, and somehow the bandwidth of the dispersion, so that is proportional to J. Yeah. Now, the Fermi velocity sits here. Yeah, so this is where the low energy modes are. But you see what happens here at the boundary of the Brillouin zone. That's lattice physics. So this is some high energy physics. So the field theory can absolutely not describe this. It has nothing to do with the field theory. So in the field theory, this thing you can just remove to infinity. Yeah, and this is what you do when you send J goes to infinity. So you remove all of the lattice physics, but you keep what happens here at low energies fixed, where you just get a linear dispersion now. Okay? So Fermi velocity I have written there, it's just this.
I think he's asking about the order of limits.
No, I'm asking, do you find the Fermi velocity just by using the low energy mode, right?
Yeah, so, I mean, the Fermi velocity is literally, I wrote it before because I told you what kf was.
Okay, and then you do the limit, setting the blood spacing.
So then I take the limit. So then now I have all of these formulas, which I wrote for you explicitly. Everything was there. Now what I'm telling you is you're free and you want to take this double scaling limit. A naught go to 0, j goes to infinity, yeah, keeping this fixed. So now j no longer exists in the field theory. And this is only just, yeah, from the field theory point of view, j is a lattice scale. It's some extremely high energy scale where the field theory can tell you absolutely nothing. So whereas the proper scale for the field theory is the velocity. The velocity basically tells you it's like the speed of light or whatever of these fermions. It's a linear dispersion. Okay? So, and in this limit, so now why do I go through all of this trouble? In this limit, if you take this, the lattice model exactly corresponds to the field theory. Yeah? And so there is a precise limit, which is this double scaling limit, in which the lattice model exactly gives rise to the field theory. No approximations, nothing, if you wish. That's not how people are using it, and that's not how we will use it later, yeah, because it's a little bit too restrictive, because that would correspond to describing really the physics has extremely large distances compared to the lattice spacing. But if you apply this to a magnet or something, okay, so you don't want to be in this limit, yeah? So you basically want to describe the physics on the scale of 100 lattice spacings or 1,000 lattice spacings, yeah? But this would correspond to the infinite distance asymptotics, just the leading term. Okay, but this is the precise limit. We will not use this in what we do later, but in this limit, so to speak, the field theory becomes exact. So that's called the scaling limit. Now, the magnetic field, I don't see any magnetic field. Where's magnetic field? Yes, 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 yes. Yeah, yeah, exactly. Yeah, exactly. Yeah. So what you do, so yeah, okay, so you're right. You want to keep capital KF fixed. Yeah? Thank you. So now what we really want to do is now turn this into a field theory. And we can do this naively, so there's nothing very subtle here. So you turn sums into integrals, that's all that happens. Yeah? And with regards to stuff like this, you just Taylor expand the fields. So the idea is you can Taylor expand the fields because they only contain low momentum modes, so they're in some sense smooth. Okay? So you have stuff like R of x plus A naught, you say is R of x plus A naught dx R of x plus dot dot dot. Well, A naught squared over 2 dx squared R of x plus dot dot dot. So you just do this. Okay? Now you just sub this in here. Okay? Now you get rid of sums and you get rid of the lattice spacing. And what you find is that the free part of the Hamiltonian now has a field theory limit, which I call curly h naught, and that's integral dx. Here we have I vf, left dagger of x dx left of x minus right dagger of x dx right of x Yeah, and then you would have actually the leading term, which would be plus integral dx. Let me just write this down, minus j cosine kf a naught plus h prime, right dagger of x, right of x, plus left dagger of x, left of x. And so then you would have plus terms which would vanish, yeah, so plus terms which would be order of the lattice spacing, but if we take the lattice spacing to 0, so they disappear. Okay? Now, the important point is that this is the leading term here, and this leading term actually precisely vanishes, yeah, because the definition of kf was that precisely this term is equal to 0. Okay? So this term precisely goes away, so the only thing that remains is this free relativistic fermion. Okay? So that's it. So this is what happens with the non-interacting part. And now we do the same with the interactions. So, okay. So now we have to deal with the interactions. And so let's look at something like C dagger J, Cj. Yeah.
The backscattering terms will be the order A naught, so that means that there will be no backscattering terms with the order A.
Ah, okay. So what I use here, it's a good question. So I had these terms. Thank you for that question. So for some reason I had skipped that. So you see these terms involving the left and right fields, they were like so. This was with the 2ikfx plus I kf a naught. So I had the terms like these. Where are you? There you are. So now these kind of vary smoothly, right, by construction, because they only have these soft momentum modes. Yeah. Here you have a rapidly oscillating factor. Yeah. So this basically oscillates extremely rapidly on a scale where this operator is essentially constant, so to speak. Yeah, and so therefore this disappears. Okay? So this is why I dropped them. Okay? Now, let's see. Now, okay, so in order to do the interaction terms, so let's look at this C dagger J, Cj. Yeah? Okay, so this goes to something like A naught. So formally speaking, I get here now something like right dagger x, right of x, plus left dagger x, left of x. And then we again have this right dagger of x, left of x, e to the minus 2i kfx, plus left dagger of x, right of x, e to the 2I kfx, where I just have multiplied everything out. Okay, so I formally get this. So now, here I have to be very careful, okay, because if I just use my projection formula blindly, I get these fields, yeah, so these are now quantum fields at the same point in space, okay? But in any quantum field theory, so these objects are a priori ill-defined, so we have to define what we mean by this. Yeah, because when you bring two fields or two operators close to one another, yeah, so the product of these operators becomes singular, and you somehow have to define what you mean by these operator products at coinciding space points. Okay, and so the way this is defined is, okay, so instead of right dagger x, right x, we introduce some normal ordering, yeah, to make this well defined. And then this is defined as the limit epsilon goes to 0 of a point split expression. So this, I assume you have seen before in your basic quantum field theory course. So whenever you have two operators at the same point, you have to point split them. And then here we subtract the ground state expectation value. Yeah, so that's how we define this object. And when we write there this naive expression, right dagger of x, right of x, we have to understand it in terms of this object here, which is now well defined. Okay? And, okay, so this is important. So I give this a name. I call this the right current J right of x. Yeah, and for left dagger of x, left of x, I have the same problem. So I should do the same for left moving fields. So similarly, J left of x. Okay, and in contrast to the right dagger right and the left dagger left, operator products like right dagger x, left of x, they're actually well defined, so I don't have to do anything. Yeah, so if you do this, it doesn't make any difference. Yeah, so there's nothing subtle about it. Yeah. No, again, you see, I have defined the low energy projection of this, this fermion operator Cj. Yeah, so this gave me the formula which I had written over there. Now I apply it blindly, naively. Okay, if I do that, then in the field theory, I get a term right dagger x, right of x. That in the field theory makes no sense. It's not well defined. Yeah? And so that basically tells me I cannot just use this boxed formula here completely blindly without giving it any thought at all. So the thing I have to be careful about, whenever I get operator products of operators at the same space point, like always in quantum field theory, I have to define what I mean by that object. Yeah, and then the standard procedure of dealing with such operator product is by point splitting. Yeah, and okay, so when you point split, you get something which is now well defined, but depends on the regulator on epsilon. Yeah, and in other words, the operator product of these two, it has a piece which is a divergent piece, like 1 over epsilon times the identity, which I subtract. And then the non-trivial part of the operator is what remains, and this is what I'm interested in. Yeah? So you'll see a little bit more of what I mean by these words in a moment. Now or later? Well, later, actually. Any other questions? No? Okay, so if I use this, I can write h int in the following way. So it becomes j delta integral dx And then here I get j of x plus a naught. And then here I define j of x is j right of x plus j left of x. Okay, so now I'm just going to write what you obtain if you now just collect all the terms in this nj plus 1 interaction term. Okay, so we have this. Then we have e to the minus 2i kf a naught left dagger of x right of x right dagger x plus a naught left x plus a naught. Okay, that is the first, and then we have plus e to the 2i kf a naught right dagger of x left of x left dagger x plus a naught right x plus a naught. Okay, and then we have two more, plus e to the 4i kfx plus 2i kf a naught. Here we get left dagger x right of x, left dagger x plus a naught right of x plus a naught. And the last one, plus e to the minus 4 chi f x minus 2i kf a naught right dagger x left of x right dagger x plus a naught left of x plus a naught. And that's it. Okay, so that's what the interaction becomes. Okay? So in other words, what you get in the field theory is precisely what you would have expected. You get a full Fermi interaction. Okay, so the interacting theory is now no longer free. Yeah, so it's an interaction between fermions, and the simplest fermion interaction you can write involves 4 Fermi fields. Okay, so this is no, again, KF. Okay, so you see, there were two KFs, as somebody spotted. There is this guy, which does not have a dimension, yeah, and there is this guy, which is KF divided by A naught, which has a dimension, and I have to compensate the dimension, yeah. And it's a good question. I mean, so you're right to be bothered by the appearance of a cutoff after I told you, we take the limit of the cutoff goes to 0, etc., etc. Now, why is it still sloshing around? Why on earth is KF still sloshing around? Is kind of a very closely related question to what you just asked. Okay? And the reason is, so KF, so the Fermi momentum, it's a property of the lattice model. Okay? And when I go from the lattice model, I go to the field theory. The field theory, in principle, no longer is just a free fermion, a free relativistic fermion. Okay? That field theory, it doesn't know about KF, because KF comes from the lattice model. But because I want to relate the field theory to the lattice model, I always have to retain this information that my field theory came from the lattice model by keeping track of oscillating terms and so on and so forth. Yeah, so in other words, I have the lattice model, and then I have the QFT. So I have something like this. So in the QFT, there is no A naught. So in a sense, you're right. But if I have an operator here in the lattice model, so Cj or something like this, I now map this onto an operator in the quantum field theory, yeah, and then I have square root of A naught, R of x, e to the I kfx, plus left of x, e to the minus I kfx. So it involves the scaling field, so the fields in the quantum field theory, but it supplements them by information about the lattice model. Yeah? And this is where these kind of dependencies of Kf, et cetera, which I need if I want to describe the physics of the lattice model, come in. When I map the lattice operator to the field theory. Yeah? Yeah. 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 It's not a rotative wave. I mean, look. You mean here? Well, it's a good question. I was just coming to this, but I wanted to explain your previous question first, right? And I think I've done that now, yeah? So because the lattice model, of course, can never be just the same as the field theory, yeah? Because the low energy modes appear at plus or minus kf, which is a finite scale, yeah? Which makes no sense in the field theory. So therefore, it arises in the map, in the low energy projection of the lattice operator when I express it in terms of the field theory. I always get this lattice data. And this is completely sensible, and it's standard, and it happens in all of these problems. Yeah, when you have a non-trivial ground state on the lattice. Okay? Now, the other question. So I was actually... that was my next point. The way I wanted to deal with this, I wanted to ask you. So, in response to a previous question, I said, well, okay, so this e to the 2I kfx terms we can drop because they're rapidly oscillating. So under the integral, yeah, they cannot make a contribution. So why on earth do I retain these? That's what you just asked, but I wanted to ask you before you wanted to ask me, so anybody, any idea? So what I did before, I told you integral dx e to the 2I kfx right dagger left, so that I could set to 0. But what I'm saying now is 4kf x right dagger left, right dagger left. So that I have to be careful. I cannot just drop it. Why can I not just drop it? So I like the word for. The rest not so much. Yeah. But what I like is okay, so think about the case without a magnetic field. Without a magnetic field, we had filled the Fermi sea between minus pi over 2 and pi over 2. Okay, so then Kf would be roughly pi over 2a naught. Yeah? And then you see this thing always oscillates on the lattice scale very, very quickly. Yeah, because 2kf would be, in this case, would be pi. Yeah, and as I go from one lattice side to the next, I pick up a minus sign. I literally go like this. Now 4kf in zero field would be 2 pi, which is 0. Yeah, so 4kf, I have to be careful. I cannot just drop it Yeah, because if I'm in zero magnetic field, 4kF is literally 2 pi, in which case this factor is literally 1. Okay, so that's why I kept it. On the other hand, if I have a strong field, yeah, then again 4kF is some incommensurate finite value. This is rapidly oscillating, I can drop it. Okay, but when the field becomes very, very small, I have to worry about it. I have to retain it. Okay, so that's why 2 drop, 4 keep. This is kf a naught. So this is perfectly, this is just some phase. It's a constant phase. Yeah? There was another question? No? So then we take the, just a sec. Then we take the break now and carry on in 10 minutes. Only nice comments, you know, otherwise we'll hunt you down. Yeah. I hope that was not recorded. Yeah. Okay. Okay. So now finally, after 7 lectures, we will bosonize. Okay, but before we do that, so the 4kF x terms, let's just write this down, can only contribute if 4kF a naught equals 2 pi, because otherwise they oscillate very rapidly in x. And this corresponds to zero magnetic field. Yeah. So if I'm in a finite field, I can drop this 4kF x terms, but in zero field, I have to keep it. Yeah. Yeah, then you have a problem, and I'm not going to discuss it. Yeah. So it's a very interesting question. Yeah, what is the effect of a small field? But you know, so already as it is, I don't have enough time to tell you everything that I need to tell you. So, okay. So now, what we can do in the free theory. So where we are going, so we saw in the fermionic language, this Heisenberg model reduces to a fermionic quantum field theory, but with interactions. Yeah. So what I have done is I have replaced one complicated model that I cannot solve by elementary means by another complicated model I cannot solve by elementary means, because I have to deal with the 4 Fermi interactions. And the trick will be to use the equivalence of the free bosons and the free fermion, and we will see that this interacting fermion theory actually is equivalent to a non-interacting boson theory, and this sorts out everything. This is where we're going. But in order to go there, let's just remind ourselves, if I am interested, let's say, in the ground state correlation functions of the right moving field in the free theory, I can calculate this exactly, minus 2IL sine pi over L x minus Vt, so it's something like this. And similarly, x plus Vt, so something like this. Okay. Just to check, I mean, so the way to calculate these, you basically just write down the mode expansion of the fields, yeah, and then you evaluate the correlation function using the mode expansion. So now, the next step is now finally we put everything together. So the next step is we do this abelian bosonization. If you don't like the t, remove it. So I can consider non-equal time correlation function, so this would just be a Heisenberg picture operator, e to the iht, r dagger of x e to the minus iht. If you don't want this, it's fine. So you can just do this. Yeah. So I'm just writing this down because it will help us to identify what operators in the free boson theory correspond to what operators in the free fermion theory. So this is abelian bosonization. Okay. So we have seen that the spectra of the free fermion and free boson are the same. So in other words, here we had the boson. Let me just remind you. So we had E was 2 pi V over L, pi squared, R squared, M squared, plus N squared divided by 4 pi R squared. And then we had plus M equals 1 to infinity, M plus M minus M. And P, we had 2 pi nm plus 2 pi over L, sum M equals 1 to infinity, minus M minus M. Okay? Well, so these terms, they came from the zero mode, these came from the finite momentum modes, etc., etc. And for the free fermion, we had the same. So here we had E minus E ground state was 2 pi Vf divided by L. Here we had M squared over 4 plus N squared plus sum M equals 1 to infinity M plus M minus M. Yeah, and then in the field theory, the momentum was 2 pi over L. In the field theory, compared to the lattice model, I just have to strip off this piece, which was proportional to 2kf, and I get Nm plus M equals 1 to infinity, M minus M minus M. Okay, so this is what we saw before. And now if you look at them, you see they agree if we take the Fermi velocity equal to the velocity in the compact boson, and if we fix this radius, the compactification radius of the boson, to be 1 over square root 4 pi. Yeah. So the free fermion is equal to the free boson for a particular value of the radius. Okay? And we see this basically from the finite size spectrum, right? So this is a very strong indication. And we can go further because we can identify operators by looking at correlation functions. Yeah, so what we saw in the free boson, I showed you how to compute two-point functions of vertex operators, and the same calculation you can use to calculate endpoint functions of vertex operators. And I just wrote down the two-point function of Fermi fields in the free fermion theory. In the same way, using Wick's theorem, you can calculate endpoint functions. Yeah, so you know all the correlation functions, and from the knowledge of the correlation functions, you can then identify which operator in the free fermion theory must be equal to what operator in the free boson theory. Okay? Yes. I mentioned this, but when I wrote it down. So yesterday we computed the spectrum of low-lying excitations of the lattice model. Yeah, and in the lattice model, I have the information about 2kF. In particular, these excitations I got by making a hole on the at the left Fermi point, putting a particle at the right Fermi point, gave me a contribution of 2kF. Okay, but in the field theory itself, there is no such thing. Yeah, so that extra piece comes from when you relate the lattice model to the field theory. In the field theory, it's just not there. You just drop it. Okay. Okay. Now you compare. Okay. So for example, right dagger of x, right of x. Would be the same as 1 over 2 pi L epsilon, as we had written it, e to the I square root of 4 pi phi right, e to the minus I square root of 4 pi phi right. Something like this. And then as I had written when we dealt with a free boson, so this L times epsilon was this smooth momentum cutoff in the free boson. I set that equal to the lattice spacing. Okay. And etc., 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 pp. So you can accommodate basically all correlation functions by, well, okay, yeah. R0, yes, thank you. That is just a typo. Thank you. It's the long distance asymptotics of correlation functions, yes. So we can accommodate this map of any correlation function to any correlation function by setting. So R of x, if you wish, is equal 1 over 2 pi a naught e to the minus I squared of 4 pi phi r. There will be one subtlety, but let me first finish writing. Yeah. So this is what I would conclude by basically just comparing these correlation functions. Now there is a subtlety, because this is a Fermi field, that is a Fermi field, so these two operators have to anti-commute, because they're both fermions. Now, the way we had introduced these chiral bosons, phi right actually commuted with phi left. So what I have here is this vertex operator commutes with that vertex operator. Yeah. So you say, oh, okay, so there's a problem. So the way you fix the problem, you introduce what is called a Klein factor. Yeah, eta and eta bar. So this is a very common trick in QFT. So these are so-called Klein factors. So these are anti-commuting variables that square to 1. Yeah, and it is this anti-commuting property of the Klein factor which then ensures that R and L anti-commute. So now everything is great. But, okay, so now you might say, well, okay, so what are these Klein factors? Do they exist? I mean, you're just writing some junk. I mean, so a very easy way is you can take eta is sigma x and eta bar, you can take sigma y or something like this. Let me see. This is what I, yeah. Yeah, so you can just choose them to be Pauli matrices, and Pauli matrices, different ones, of course, they anti-commute and square to 1. Now, okay, so those are the operator equivalences. Okay, and now the obvious question that arises, I have introduced additional degrees of freedom, namely these Klein factors. Yeah. And so these are operators that act on a two-dimensional linear vector space. Yeah, so they act on, let's say, up and down, which means by using this trick, I have introduced some unphysical degrees of freedom. I just need them in order to ensure the correct anti-commutation relations, but I have introduced these additional degrees of freedom. Now, any physical property, any physical quantity cannot depend on this Klein factor business. So basically, the way to treat with this, any expectation value of a physical operator, you always impose an expectation value in this Klein space. So you take the expectation value, say, with respect to this up state. If you prefer, you can take expectation value with respect to the down state, or you can take the trace, whatever. So you just have to average over these degrees of freedom, and that removes this unphysical part of the Hilbert space and gives you the final answer. Okay? Okay, so now this was at the level of the free theory. So free boson equals free fermions. Yeah.
So if I average over only the up state and I just get an eta, this average will zero.
Sorry? Yeah, exactly. And that's a good thing because, well, so the average of the Fermi field better be 0. Yeah, so this is nothing to worry about. So it's more if you have something like here sigma a, so if you have something like eta bar, which will pop up in a moment, yeah, so that will have an expectation value. And all that gives you, it gives you an extra factor of I or something like this, but you have to keep track of it. So I want what I said I want. Yeah. So I introduced this to give me the anti-commutation relations, but now all my operators involve these Klein operators. Now, when I compute a correlation function, yeah. So let's say I compute right dagger of x, right of x, right of 0, yeah, okay. Yeah, so you will get something here on the right-hand side, but you will get something like eta bar. Yeah, or, and I have to define what that is. Okay, and what I said is I define this to be simply this. Okay, and if I do that, then correlation functions map 1 to 1. Okay? Not right dagger right. So right dagger right dagger left. So if I had something like this, left of 0, yeah, so if you have this product, not the other one, in the other one you would have eta squared, which is 1, it would drop out, sorry. Yeah. Okay. Okay, so these Klein factors, it's a very general trick in theoretical physics. So whenever you have a problem with having to ensure anti-commutation relations, you introduce these Klein factors. Okay, now, yeah, yeah. Yes. Okay, so no. So look, the Klein factor is a very trivial thing. Yeah, there is no x dependence, nothing. So this is an overall phase factor, if you wish, that the Klein factors give you. All the complicated dependence of the correlation function of x and t, it comes from these fields. Yeah, so the Klein factor, it's a very minor modification. Yeah, so it ensures the correct anti-commutation, and it ensures that any correlation function in one theory is equal to the correlation function in the other theory. Yeah, and if you look at the Hamiltonians, you can use this description in the Hamiltonians. The Klein factors drop out. Yeah, so the energy levels, momentum levels are not affected by the Klein factors, so this identification of the spectrum is unaffected. Okay? So this is one way of doing the map free boson to the free fermion. It's not the only way. So if you look at the literature, there are other kind of choices of making the identification. So what you can do is you can change your definition of the zero modes of the compact boson in such a way that you don't have to introduce these Klein factors. Yeah, so that's a choice, it's a convention. But our choice, our convention, it's fully consistent. So this is one way, one of the standard ways of doing it. So, okay, so I have a little bit of time. Okay, so now we start doing, we come to the business end. So now we have to bosonize the interactions. Okay, so let's start with this operator product that we had quite a few questions about. Yeah, so the right dagger x, right of x. So now I'm going to treat this explicitly. So this is the limit epsilon goes to 0, right dagger x minus epsilon, right x plus epsilon, minus right dagger x minus epsilon, right x plus epsilon. That's how it was defined. So now let me work this out using my bosonization description. Yeah, so to work this out, what we use is the following. So we use e to the minus I square root of 4 pi phi right of x, e to the I square root of 4 pi phi right of y is equal to a normal ordered vertex operator e to the minus I square root of 4 pi phi right of x minus phi right of y times an extra factor, and the extra factor is I a naught divided by x minus y. And we're interested in the limit x minus y goes to 0. Okay, so how to multiply vertex operators I told you before, I showed you before. Yeah. And now I just use that identity that we derived for the free boson in precisely this form. Yeah, so I multiply the vertex operators on the right-hand side. Now I get another vertex operator. I normal order that, so I get an extra factor. Yeah, so this we discussed before. And for phi left, we have something very similar. Well, all right, so I can... So this is the normal ordered one. And then here we get an extra minus sign. Okay, so this you get from the formulas we had in the limit when x minus y is much less than the physical length of the ring on which the free boson is defined. Okay, now we use this. Yeah, and then you will immediately understand why we have to do this point splitting, etc., etc. Because what I get here on the right-hand side is the following. So I have 1 over 2 pi a naught, which comes from the definition of the right Fermi fields in terms of the bosonic vertex operators. And then here I get, well, okay, so e to the I square root of 4 pi phi right of x minus epsilon e to the minus I square root of 4 pi phi right x plus epsilon minus the expectation value. And this is the limit. Now I use this formula up there, so I get here the normal ordered vertex operator e to the I square root of 4 pi phi right x minus epsilon minus phi right x plus epsilon. Yeah, and then from here, I get an extra factor, a naught divided by 2I epsilon. And then I get minus the ground set expectation value, but the ground set expectation value of a normal ordered vertex operator was just 1. Yeah. So this is minus minus a naught divided by 2I epsilon. Yeah, that's what I want to write. Okay, and then the last step is, now you Taylor expand here in the exponent, so this becomes minus 2 epsilon d x phi right of x plus dot dot dot, higher order terms. Okay, and now you can expand this exponential. You see the leading term is just 1. And then you get a divergent piece in the limit epsilon goes to 0. But it's precisely cancelled by what I subtract here. And that's why I had to point split and do the subtraction. So to get rid of this kind of trivial contribution. And then what I remain with is then the first order term. But you see the first order term, the epsilon precisely cancels. So now we have a finite limit. And that limit is minus 1 divided by square root of pi dx phi right of x. Okay? So that was kind of nice. So now similarly, we get left dagger of x left of x, defined in this point split subtracted way, is minus 1 divided by square root of pi dx phi left. And so this tells us that this operator, which we had called j of x, which was the sum of the two terms, that is just minus 1 over square root of pi dx phi. Okay? So now, already at this point, you can see there is some magic going on here, right? Because in the fermion model, this operator J was quadratic in fermions. And we had explicitly in the interacting Hamiltonian a 4 Fermi term, J of x plus A naught. So that was an interaction term. But in terms of the boson, J is just dx phi. So therefore, that particular 4 Fermi point becomes something quadratic in the Bose field, which just adds to the free boson Hamiltonian. Okay, so I had something which is a fermion interaction that has mapped just onto a kind of kinetic term for the boson. And that's the magic of the bosonization. Okay, so now the other bilinears, they go like so. Right dagger x, left x is, here I have to keep these Klein factors. E to the I square root 4 pi phi. And left dagger x, right of x is eta bar eta 2 pi A naught e to the minus I squared of 4 pi phi. Okay? So these are not so nice. Sorry? Yeah, but the normal ordering of phi is the same as phi. For the? And that gives me a normal ordered dx phi. And there is no normal ordering involved in dx phi because there is no, it's linear in terms of creation operators and annihilation operators. Yeah? So I just dropped it because I could. Okay. So now I go until 11. Yeah? No, until when do I go? No, that's fine. I'm asking, I just don't know. Yeah. 10 to 11. Yeah. No, I'm not asking to go longer. I mean, I just ask when I have to stop. Okay, so now in order to work out the terms in the interaction Hamiltonian, I have to take products of operators like these. Yeah, so for example, so then we can compute now something like this. Right dagger of x, left of x, left dagger of x plus A naught, right of x plus A naught. Yeah, so that was one of the terms in the interaction Hamiltonian. Okay, and now I can just use these formulas and multiply them. Yeah, and then you see what you get is this becomes 1 over 2 pi a naught squared. And here I get something like e to the I square root of 4 pi phi of x minus phi of x plus a naught. Yeah, and you see the Klein factors will disappear because you get eta, eta dagger, eta, eta bar, eta, but eta bar squared is 1 and eta squared is 1. And now I do the same trick I did before, so I Taylor expand the exponent here, yeah, because x plus a naught is essentially the same as x, so this becomes the same as constant. Now minus I divided by 2 pi 3/2 a naught dx phi, and then the next term I get is 1 over 2 pi, and here I have to keep the normal ordering, dx phi squared plus dot dot dot. So higher orders in a naught, so to speak, which I will drop. Okay, and the others you can treat similarly. Left dagger of x, right of x, right dagger of x plus a naught, left of x plus a naught, so that becomes constant, plus I dx phi divided by 2 pi to the 3/2 a naught, minus 1 divided by 2 pi dx phi squared, and finally we have this left dagger of x, right of x, left dagger of x plus a naught, right of x plus a naught. So this basically gives rise to something like minus apparently 1 over 2 pi a naught squared. And here I get normal ordered e to the minus I square root of 16 pi phi. And the last one, so, and that's it. Okay, and now this tells us that the interaction part of the Hamiltonian becomes j delta a naught, yeah, integral dx 2 over pi sine squared kf a naught dx phi squared plus sine 2kf a naught pi to the 3/2 a naught dx phi, and one more term, which is 1 minus 2 pi squared a naught squared cosine square root of 16 pi phi minus 4kf x plus a naught over 2. Okay, so this is the upshot. Okay? Now, I have 2 more minutes, which is perfect. And of course, I will keep on having 2 more minutes for the next 10 minutes. Okay, now this term we're happy with, right? Because it's quadratic in the bosons. This term we're happy with, yeah, so we can deal with it very easily. It's linear in the bosons. Now, what about this term here? Yeah, so this is one of these bosonic vertex operators. So now, here we have a 4kfx factor. And as we said before, in finite magnetic field, this is rapidly oscillating in x. So I can just drop this term. However, in zero field, which is a case I'm very interested in, 4kfx is just 2 pi. Yeah, and I cannot use this argument. So this term is not rapidly oscillating. I have to keep it. So I get something like cosine square root of 16 pi phi. Now we use what we learned about Rg. Yeah, so if we have a free boson and if we're perturbed by a cosine operator, yeah, cosine beta phi, then if this beta is larger than square root of 8 pi, that perturbation is irrelevant in the Rg sense. Now, cosine of square root of 16 pi is larger than square root of 8 pi, which means this will be an irrelevant perturbation at small interactions, so I can drop it. Which means, in all cases, the term I would have trouble to deal with, because it's a non-trivial deformation of the boson theory, is not there. Okay? And that makes us very happy. So I'm just going to write that down. So, dot, dot, dot. So that's the discussion I just gave you. So then the Hamiltonian becomes h naught plus h int is Vf divided by 2 integral dx. So here we get 1 plus 4 delta over pi sine kf a naught dx phi squared plus dx theta squared. So theta was this dual field, phi right minus phi left, and then we have an extra contribution j delta sine 2kf a naught divided by pi to the 3/2 integral dx dx phi. So that's what we have found. So the interacting fermion theory has reduced to a free boson theory, hallelujah. So now you have mapped the complicated model to a simple model, and in this simple model you can compute everything. Yeah, and that's the magic of bosonization. What I will do tomorrow, I will massage this a little bit. So in particular, you can remove this term. You might think, well, it's a total derivative, so I can just drop it. It's not quite as simple as that. It has an interesting effect, which I want to emphasize tomorrow. But then we end up just with a free theory, and then we will use this free theory to compute spin-spin correlation functions in the lattice model, which will be kind of nice. Okay? And then now I stop.